Welcome to the third session on polar plots. We have studied polar plots in last two classes, and this is the third class on polar plot, and we are going to study two loop transfer functions here. The first transfer function is GSHS equal to k divided by s into tau s plus 1, and the second transfer function is k divided by s into tau 1s plus 1 divided by tau 2s plus 1. So we start with the first one, that is the k divided by s into tau s plus 1. So as usual, we assign s equal to j omega. So we have g at j omega, h at j omega equal to k divided by j omega into tau into j omega plus 1. This is again equal to, after expanding the bracket, we get the negative term where we have j square and the positive term, that is the imaginary term. So we can write like this: j omega, the second term written first, and tau omega square. So this can again be written by multiplying numerator and denominator by minus 1. We can write it k divided by minus k divided by tau omega square minus j omega. So this rational complex number, so we can write g at j omega, g at j omega, h at j omega equal to minus k. So this complex term is multiplied by its complex conjugate in the numerator and denominator. So we can write tau omega square plus j omega, and denominator will be tau omega square. So that will be the formula of a plus b into a minus b equal to a square minus b square. So this is whole square plus omega square. Again, g at j omega, h at j omega, this should be equal to k divided by square root of, I am writing omega square first, then the tau omega square term. You see, if we want to take the magnitude, the numerator, the magnitude will be square root of omega square plus tau omega square whole square. So numerator and denominator, one radical term will be cancelled, and numerator, one radical term is left, and this will be accompanied by the angle, that is the phase of the transfer function, that is tan inverse of imaginary part divided by real part. So that becomes 1 divided by tau omega, because omega by tau omega square, there omega is cancelled from numerator and denominator. So from here we can write in magnitude and phase for omega equal to 0 as well as omega equals to infinity, and in between, if there are some critical frequencies, we should write the magnitude and phase for that frequency also. So from here we can write further, for limit omega tends to 0, you have g at j omega, h at j omega equal to, you see here denominator becomes 0, so magnitude would be very high, and here again that is why this comes minus 90 degree, that is tan of 90 degree is infinity, so minus sign is there in front of tan inverse. Similarly, we can find out the magnitude and phase for infinite frequency. So we will start plotting at infinite, plotting at 0 frequency and reach up to infinite frequency. So omega tends to infinity, g at j omega, h at j omega, this should be equal to, now here you see the omega value is very large, so magnitude is almost 0, but here you see, because of the minus term in front, it will become angle of 180 degree, right? So again we can draw the plot for it. See, can have the real and imaginary axis like this, the real and imaginary axis like this, and there you have to write very clearly real part of g at j omega, g at j omega, h at j omega, and imaginary part of g at j omega, h at j omega. Why I have drawn like this? The first quadrant and second quadrant are smaller in size because the graph will start from the third quadrant. So for omega equal to 0, as we have seen, you can see that for omega equal to 0 the magnitude is infinity but angle is minus 90 degree. Here you can see the angle is minus 90 degree and omega equals to infinity. So we start from minus 90 degree and infinite magnitude, so we can start from below, from here, this point, and we will gradually grow and reach up to the origin at angle 180 degree. So naturally this angle is 180 degree where we are entering the origin, and starting this is minus 90 degree. This angle is minus 90 degree, minus 90 degree. So we are starting from omega equal to 0 and reaching at omega equal to infinity. So this is how we should draw the polar plot for GS HS equal to k divided by s into tau s plus 1, where s equal to 0. So this is how polar plot is drawn for the first transfer function. Now going to the second transfer function is like this. We have g at j omega, h at j omega equal to k divided by, because s is j omega, so we again write s is j omega. Now tau 1 s plus 1, tau 2 s plus 1, so tau 1 s will become tau 1 j omega plus 1, and tau 2 s will become tau 2 j omega plus 1. So this is the transfer function. Again we have to take the rational form by multiplying all the terms and expanding, so we can do it steps. So this is equal to magnitude of 1 divided by, that is k divided by j omega, j into tau 1 omega plus 1 j into tau 2 omega plus 1. This magnitude multiplied by the phase. So what are the different phases? The phase for tau 1 omega plus 1, this when it is rationalized, it should be rationalized in such a way that this is compensated by its complex conjugate, so that will be minus j tau 1 omega plus 1. Its complex conjugate should be minus j tau 1 omega plus 1. This is the complex conjugate, so that will be in the numerator. So for that the phase angle should be minus tan inverse tau 1 omega. Similarly for the second one, this one, that is actually this is the third factor, for this it will be minus tan inverse tau 2 omega, and the first term 1 by j omega, that will naturally become minus pi by 2. So that is how the phase angle can be determined. Now and see how this bracket in the denominator is solved further. So you can take it like this: g at j omega, g at j omega, h at j omega equal to k divided by j omega into 1 minus tau 1 tau 2 omega square. I am expanding the brackets, plus j tau 1 plus tau 2 to omega, bracket close. So on expanding, we will find there should be all these 4 terms in the denominator, and that can further be written as k divided by see the imaginary terms, those will be separated from the real terms. So when you multiply j omega, the j into tau 1 plus tau 2 omega will become real. So because of the j multiplied this j multiplied by this j, it will become minus 1. So we can write like this: minus tau 1 plus tau 2 omega square plus j of omega into 1 minus tau 1 tau 2 omega square. So you are getting the expression simplified. Now this can be written in the form of complex conjugate of this multiplied to the numerator, and the denominator will be rationalized. So by this time you should have understood, you must have understood that the magnitude of this will give you exactly the same thing which we can get by getting the rational complex number. So how we can do it? See, this term can be written as g at j omega, g at j omega, h at j omega equal to k divided by phase. We have already determined, phase is already determined, so denominator is square root of exactly omega, first term tau 1 plus tau 2, this is multiplied by omega square, so that will again be squared. So this is squared plus omega is squared, so that will become omega power 4 plus omega square, second term squared, 1 minus tau 1 tau 2 tau 1 tau 2 omega square whole square, complete radical sign over it, and above it we have already estimated the phase, tan in minus tan inverse of tau 1 omega minus tan inverse of tau 2 omega and minus pi by 2. So this we can give the bracket for clarity. So once we have achieved this, we can write it in the form for different values of omega. We say limit omega tends to 0, how this magnitude and phase should come: j omega h, g at j omega, h at j omega equals to, see, numerator is constant but denominator is having a lot of omega terms, so naturally the magnitude becomes infinity. Here again omega equal to 0, so only minus pi by 2 is left. Now coming to limit omega tends to infinity, g at j omega, h at j omega, this is equal to, so naturally denominator is having omega, so omega is infinity means magnitude is 0. Now all the three terms are minus pi by 2. Naturally you can say first term is minus 90, second term is minus 90, third term is minus 90. So this is naturally becoming minus 3 pi by 2. We are getting, basically we are crossing the axis, which is the negative real axis. So there are important crossing points, how we can determine the magnitude and phase and frequency at that crossing point. So for that we should go like this. Imaginary part will be Im g at j omega, h at j omega, this should be equal to 0. So once I equate this with 0, it means we have minus omega into 1 minus tau 1 dot 2 omega square equal to 0. So from this we understand that omega should not be 0 at the crossing of imaginary axis. So 1 minus tau 1 tau 2 omega square should be 0 implies that omega equals to 1 divided by square root of tau 1 tau 2. So from there we can determine what is the uh, component on the negative real axis which is traversed. So for that we can very easily write real part of g at g omega, h at g omega, and assigning omega equals to 1 by square root of tau 1 tau 2. So if we assign this and simplify the real part, so imaginary part should be 0 in the expression, only real part will have value. So from there you can find out very easily that this is equal to minus k tau 1 tau 2 divided by tau 1 plus tau 2. I expect my students to try this themselves. However, I am sending them the detailed notes. From there they can. It's advisable that they do the things themselves. So equal to, I advise my students to try solving this by their own. So because of that, this should be equal to minus k divided by 1 divided 1 plus 1 by tau 1 plus 1 divided by tau 2. Like this it should come. So from here further you can draw the polar plot for this. We have the imaginary axis. Again we will give more place for the third and fourth quadrant. So this is the imaginary axis. We write very clearly real part of g at g omega, h at g omega, and imaginary part of g at g omega, h at g omega. So once we plot, again we will start in the like in the previous case at omega equal to 0, it is magnitude is infinity and angle is minus 90 degrees. So we start somewhere from like this and it will go very smoothly. Draw it again. So it should go very smoothly and should cross the imaginary axis and reach the origin at minus 270 degree. So minus 270 degree is like this. You are entering the origin in this direction and starting from here. So omega equal to 0 you are starting and omega equals to infinity you are ending. So in between we have determined the crossing point. This is the real part, the negative side it is traversing. So we can very well mention that this is the frequency omega equals to 1 by root tau 1 tau 2 and this magnitude is minus k divided by 1 by tau 1 plus 1 by tau 2. So this is important, the crossing point you should write very clearly. So this is the polar plot for GS HS equal to k divided by s into tau 1s plus 1 and tau 2s plus 1 for s equal to j omega. So this is how we can draw the polar plot for k divided by s into tau 1s plus 1 into tau 2s plus 1. So the difference between the polar plots of k divided by s into tau s plus 1 and this polar plot, you must have observed it carefully. So more the number of poles increase, the more will be the crossings of the axis. So if from this we can understand that if there are more poles, so there will be more crossings of the axis. and again an angle will be changing. So for today these two plots we are discussing, and for my students I will share few more examples through notes, and in the next lecture we shall discuss an important example on polar plots. The textbook written by Professor M. Gopal on control systems can be referred to. Another book on control systems written by foreign authors and adapted by an Indian author, Professor Sanjay Mandal, is a good example of simple language textbook which can be referred. Another example of the book on control systems by Professor Syed Hassan Saeed of Integral University Lucknow can also be referred.